Here we go. Supplemental assignment number 1 is our introduction to nuclear chemistry. That's the chemistry of the nucleus. So we start with defining what we have. The nucleus of an atom contains protons and neutrons. The protons are positively charged. The neutrons have no charge at all. Here's a little picture in the corner here of a nucleus. Protons are positive, neutrons have no charge. You'll notice that it says protons repel, so there must be another force here that binds this structure together. That force is the strong nuclear force. It is more powerful than electrostatic forces, which are the plus-minus forces that are mostly important in chemistry. So this is stronger, able to overcome the repulsion, but works only at very short distances. The atomic number. If we look at the periodic table, we have for each element an atomic number on the top, which is a whole number, and an atomic mass on the bottom, which is not a whole number usually. So the atomic number is the number of protons. That has to be an integer. The atomic mass is the protons plus neutrons. So it's a sum. And you may still be thinking that it should be a whole number, which is correct. Since each of these are integers, we should get a whole number sum. However, this next concept can explain why we get on the periodic table masses that are not whole numbers. And this is because each element has various isotopes. Nuclei with different masses. So I'll try to teach this through example. Here's hydrogen. Hydrogen on the periodic table has an atomic number of 1, has a mass of 1.0079. Every hydrogen has 1 proton and a varying number of neutrons. So this symbol you haven't seen before. We have a number in the lower left. That is the number of protons, or the atomic number. The number in the upper left is the atomic mass of that particular isotope. So this is hydrogen with a mass of 1. The nucleus must contain 1 proton and 0 neutrons. Hydrogen with a mass of 2 must contain 1 proton, otherwise it wouldn't be hydrogen. But then this nucleus also has a neutron, so the total is a mass of 2. Hydrogen with a mass of 3, 1 proton, 2 neutrons. So here we see 3 different isotopes of hydrogen, H1, H2, H3, sometimes called deuterium, deutero meaning 2, sometimes called tritium, tri meaning 3. And if we understand that these are all part of naturally occurring hydrogen, then we can understand the mass on the periodic table being 1.0079. The vast majority of hydrogen isotopes are mass 1, but there are a few, a very small percentage that are mass 2, and an even smaller percentage that are mass 3, and that is why this number on the periodic table is above 1. This is the average of the isotopes found on our world. So now, if we look at isotopes of carbon, you have a chance to practice your skills before I fill this in. So if you'd like to practice your skills, then pause the instructional video, you try, and then check your work with my instruction. Since carbon here has an atomic number of 6, the mass of 12.011, every carbon must have 6 protons. So here we see carbon with 6 protons, mass of 11. That would be 6 protons plus 5 neutrons. If the mass is 12, which is the vast majority of carbon atoms on our planet, that's 6 protons and 6 neutrons. If the mass is 13, that's 6 protons plus 7 neutrons. And if the mass is 14, 6 protons plus 8 neutrons. So you can see here that these are different types of carbon atoms. They differ in their nucleus. Since the atomic mass on the periodic table is 12.011, it should make sense to you that most of the carbon atoms are mass 12. The next most abundant isotope is carbon 13. About 1% of the carbon on our planet is carbon 13. Now we get to talk about stable versus unstable nuclei. Some nuclei are stable. Sort of the normal form is stable. And when we get abnormal forms, they're called unstable isotopes. And unstable isotopes are radioactive. Unstable isotopes are radioactive. Carbon 12 and carbon 13 are stable isotopes. That is why on the periodic table our mass is 12.011. Those are the ones that are very common. The unstable isotopes are not very common. Carbon 14, carbon 11 are unstable isotopes and are very rare. If an isotope is radioactive, if the nucleus is unstable, then it does what's called a decay process. It changes. It becomes stable by changing itself. So these are natural processes. The first form is called alpha decay. Second is beta. Third is gamma. These are the first three letters of the Greek alphabet. You've seen alpha particles before. So in alpha decay, a nucleus splits and shoots out an alpha particle. The symbol is this squiggly A, which is the Greek letter alpha. Alpha particle is actually a helium nucleus. So you saw these in the Rutherford experiment, if you'll recall. Helium nucleus has 2 protons and 2 neutrons. In every alpha decay, an alpha particle will be shot out from the nucleus. The second type of radioactive decay is called beta decay. In this case, we have a strange change occurring within the nucleus. It transmutes so that a neutron becomes a proton. A neutron becomes a proton. So this is very strange. A neutron has no charge, a proton has a positive charge. So in order to obey the rule of for every plus there is a minus, there is, at the same time the proton is created, an electron is created. So you can kind of think of this as neutron becomes proton plus electron. And maybe we'll emphasize that this is a positive. So you can see it adds up. For every plus there's a minus. The third type of decay is called gamma decay. So this deals with the concept of excited states. We saw this in the photon game, how electrons could be excited within an atom. Now we're saying the nucleus itself can have quantum states, and there can be a nucleus in an excited state. Shoots out a very high energy photon. These would sometimes be called gamma rays. Gamma rays. And this, I believe, is what created the Hulk. Now we're trying to write these nuclear decay processes with symbols like a chemical equation. So here's the first example. U is uranium. Uranium is way down here on the periodic table, but its atomic number is 92. It's radioactive. All forms of uranium are radioactive. And if it's alpha decay, then we must get the alpha particle, which is the helium nucleus, 2 protons, 2 neutrons, so a mass of 4. To find this remaining nucleus, the second product, we simply do math, very simple math. 92 protons originally, 2 protons in the helium nucleus leaves 90 for this nucleus. Mass-wise, same thing. 238 total mass, take away 4, leaves you 234 mass. To find the letters, I look at the periodic table. Element number 90 is TH. It is called thorium. The thunder god names Thor. This is thorium. So there's an example. Here's our second example. Radium has 88 protons, but take away 2. What's left is 86. How about the mass? 224, take away 4. The mass is 220. To find the symbol on the periodic table, I need to see who is element number 86, which happens to be the letters Rn, and that is radon. Radon, Rn. That's a noble gas, but it's a radioactive noble gas. And you may notice that the mass on the periodic table does not match the mass that I wrote here, and it doesn't have to. This is an unusual isotope of radon. Here's now beta decay. Carbon, 6 protons. If it's carbon 14, it has 8 neutrons. So this is an unusual, unstable isotope of carbon. In beta decay, a neutron becomes a proton. So here we'll have 7 protons and 7 neutrons. So that is nitrogen with a mass of 14. We've changed from carbon to nitrogen. And this is something that's very strange. If you had a lump of carbon, and you suddenly saw it evaporating into nitrogen, you'd say, my goodness, what is happening? And in this world of nuclear chemistry, it is not implausible to say, can we turn lead into gold? In a nuclear process, that is possible. All right, try your skills on this one. If you want to pause the tape, you're welcome to do so. Beta decay. Phosphorus. How many protons? 15. In the beta decay, a neutron becomes a proton, so we'll end with 16 protons. 16 neutrons. That's sulfur with a mass of 32. We've created a proton. At the same time, we create this electron. The electron is shot out like a bullet from the nucleus. So this is a strange nuclear process where an electron comes out of the nucleus, fired away like a bullet. And this is what makes radioactivity dangerous. This alpha particle is also fired out like a bullet. The danger of the radioactivity comes from these bullet-like projectiles, and they differ in their ability to penetrate through matter. Alpha radiation turns out to be very easy to stop. Hold up a piece of paper and you have shielded yourself from alpha radiation. So this is usually only dangerous if it happens inside your body. For example, if you were to breathe in radon gas, then you can't shield yourself from that internal radioactive decay. The next form of radiation, beta radiation, is much harder to stop. The particle is small. It's a high-speed electron. It therefore can go through what we consider solid material. So it can go through paper, and it can go through cardboard, it can go through your clothes. It may even go through your entire body. But it's typically stopped with perhaps a shield of lead. If you go to the doctor's office and you wear that lead shield, it's to protect you from radiation. And this second thing says plexiglass, which is a transparent shield. So you could be working behind a plexiglass shield you can still see, but you will not be irradiated with beta particles. The last form of radiation, which is gamma, is very difficult to stop. So here the suggestion is, if you want to shield yourself from gamma rays, you better have a thick lead wall. The last one here, I believe this may be the most famous equation in all of science, E equals mc squared. It comes from Einstein's theory of relativity. In this equation, mass and energy are equated. And what this means is that if you have a nuclear process, for example, that apparently creates energy, there will be a loss of mass. And so the products of a nuclear decay weigh less than the starting materials. The opposite is even more strange, that with energy, if you have a lot of energy, you can create mass, you can create matter, you can create particles. And this is what was done recently at the Super Collider at CERN in Switzerland, where they created the Higgs boson using very high-speed collisions. So the equation itself, energy and mass, are not entirely separate ideas. They are linked. E equals mc squared.